my name is Alexey Makeev, and today I will talk about rendering, and will try to share my love in rendering with you, inspire you to maybe learn it. A couple of words about me. I work in Luna, as Anton mentioned. In Luna, we are building JavaScript WebGL engine for playable ads. And now we are part of Unity Technologies portfolio of advertiser tools. So we essentially building an engine which allows us to run Unity games on web. And let's talk about rendering. So first of all, we have the screen, we have CPU, and you can pick your favorite programming language, on the CPU side, okay. And now you need to actually fill each and every pixel on your screen with some color. And color is just RGB channel for each pixel. And now things become really interesting because you need to come up with a strategy, approach. How exactly will you fill up this screen with colors? And the most obvious approach is, okay, colors is lighting is just rays. So okay, let's cast a ray from each pixel in the screen, and whenever it will hit any object in our scene, we will just get the color of this object and we'll fill it in our pixels. And why only limit with one ray cast when we can actually bounce these rays? And instead, whenever we hit one object, we cast another ray in absolutely random position, in this hemisphere. If we encounter, for example, light source, it actually means that this previous pixel was lit. If we actually never hit any light sources, this area is obviously not lit and in shade. So if you ever worked with 3D software, whenever you see such noisy image, then you can actually imagine that ray tracing is happening. And why we see all this, some of pixels are just black, is because we are missing with some rays because we are casting them randomly. But after we are applying some denoise, you can actually see what kind of image such approach can produce. First of all, I would like to highlight you that some colors are bleeding from this red sphere, so we can see this reddish color here. We can see really smooth and soft shades here. And overall image with all this lighting just looks amazing. And the approach itself is really simple. You just cast rays here and there and collect information from it. But there is one huge caveat here. Such approach is really computationally heavy. So and it completely doesn't fit for rendering purposes because hey, one image can be rendered in hours. So that kind of doesn't work for our purposes of real-time renderers. And another approach here is okay, let's grab all our objects one by one. Let's find a way to understand where exactly on the screen this object will occur. We will come up with exact pixels this object will use, and then we will just color them all. And whenever you will try to do that in your just CPU programming language and so on, you will also quickly come up with performance issues, because if you haven't considered it yet, we have 2 million pixels on the screen. We need to render them 60 times per frame, and we need to fill up 3 bytes of color. And essentially, we need to produce this amount of information each and every frame. This is insane amount of information. And nowadays, gamers obviously want hey, let's do it 4K, or let's do 120K, or 120 frames per second. Yeah, but it's really computationally heavy. And when you do it on CPU side, it's gonna look something like this. This is why industry actually pretty quickly came up with a solution. Like, okay, let's power up with another hardware device. And GPU is actually another chip in your computer, which works pretty in parallel with CPU side. It has completely separate processing units. It has completely separate memory. And it just like specified just for rendering tasks. But what actually means specified for rendering tasks? So like, if you consider CPU has a really vast number of basic commands, like for like programming purposes. GPU doesn't need to be so like common. So this is why GPUs are focusing on exactly like mass operations. Plus, as we're gonna do mass operations a lot, we need to utilize some different approaches like SIMD. So SIMD is like single instruction multiple data approach, when instead of doing, for example, like 4 additions or 4 multiplications, we can do all of them in one like tick. Also, like it would be nice if we are able to parallelize like all our computation. So like GPU are built with this idea in mind. But the main limitation here is that, like, when we were speaking about ray tracing, in order for the tracer to work, we need to know about like every object in the scene, because we're gonna recast against all the scene and check what happens there. GPU actually cannot afford such approach. This is why GPU is always working in context of only one primitive or triangle, because like triangles are like the most easy and simple like surface geometry. And GPU also has really limited amount of memory for some additional information we can pass and for additional textures. So let's go ahead. So okay, let's try do something like with GPU. First of all, like GPU sees the screen in so-called like clip space. So like it's just a mapping for the screen. And like simplest program, we need to define a triangle for it. So like we define this, like first vertex is here, second one is here, and third one is there. And voila, we have like a triangle on the screen exactly. But actually, like when we are working with 3D applications, we really want geometry. We really want some like geometry models. So 3D modeling software actually like produces models, and models consist of, first of all, like vertices, corners of geometry with positions, because we really need to understand like where exactly each corner of this model will occur. But then, like, you will come up with this problem. Like, okay, we have a cube. Cube has like a bunch of vertices here and there, but we can come up with like multiple different ways how we can like pick up triangles. So, for example, 1, 7, 4 might also be a triangle, but we don't kind of need this diagonal at all. So this is why we need also provide some triangles or indices array for GPU that, hey, please connect these 3 vertices in a triangle, the next 3 vertices in another triangle, and so on. So like we literally connect the dots by their indices. Also, 3D modeling software can bake colors for each vertex. So like we can easily color our geometry. But what is more fancy, we really want to apply some texturing over it, right? And then we need to come up like with a way how exactly we will get information from a texture, like from this texture, for each vertex like in our model. And essentially, like if you ever try to like build a cube like in an origami or like with a paper, you can come up with such shape, and like all vertices is here. And we just map that each vertex from like original model will be placed in this exact location in so-called texture coordinates or UVs. And as easy as that, we will be able to identify colors like for each pixel for each vertex. And what about like more complex models? It's exactly the same. We just unwrap our geometry into flat surface of a texture and assign each vertex or each corner with exact UV coordinate in texture. Also, 3D modeling software provides us with some extra information about normals. And normals are really essential in 3D graphics. Normals is a vectors which shows where all like triangles or geometry is facing. So like essentially gives us orientation in space for all triangles. So like all this information is stored like per vertex basis or like in each vertex. Okay, so like we got our like model from 3D modeling like software, and we need to like work with it like in the engine or wherever. So like first of all, like in our like games, we want to be able to move our objects around, like rotate our objects around or scale. Okay, and then we need to somehow like apply these transformations. And here is like where linear algebra and all the math comes really handy, because all these operations are actually linear. So like you can see in background that all the lines are staying lines. So like they are not curves after these operations. So like all three operations of like translation or like moving objects around, scaling it or rotating it can be described as matrices. And what is really amazing about it, you can actually multiply it in one matrix and just use it as one matrix. And in Unity, it's called TRS matrix, or like transform rotation scale matrix. And as the models from 3D software describe position of each vertex from like model coordinate system itself, like we need to come up with like final position for each vertex in actual scene we have. So like apply actual transformations we set in our transform. And to do that, we need to multiply each vertex position by this model matrix, and that's it. We will get coordinates in the world. But typically, when we are working with like 3D applications, we have our like virtual camera. It flies somewhere in the scene, and obviously, to present something like from eyes of camera, we need to somehow get coordinates relative to this camera, right? And yeah, like in real world, we cannot move objects around, but from computer graphic perspective, it's really easy for us to actually grab all the vertices around the world and actually convert them to camera space. And this operation is exactly the same operation we did with like converting model from like model coordinates to world coordinates. So we just multiply on another matrix, and voila, we have coordinates for like within the camera space. But okay, now like we still have some coordinates in the world, but we need to somehow get this object on the screen. And this operation is called projection, and there are multiple projections out there. The two most common ones are orthographic projection, where we actually don't like change the size of objects like depending on like the distance. So typical example for such projection matrix application is like isometric games, right? So like you can see that all sides of these cubes stay the same like after this projection. But typically for 3D applications, perspective projection is used. And what does it mean, perspective projection? Perspective projection, like example similar to previous one, actually handles this effect that more distant objects from us appear smaller, right? So after we apply our like projection matrix here, you can see that objects which were cubes are actually changed like in shape. And from perspective of like camera now, you can see this is how it looks like. So more distant cubes appear actually smaller and in our like clip space. And then GPU automatically handles like resolution conversations for us. But what is absolutely exciting about it is that GPU actually allows us to control it in code. So essentially, like as we start from like random CPU like based language, developers of GPU actually allowed us to write GPU code. So this GPU code which actually are running on GPU side is called shaders. And we can actually run this shader program for like vertices and for each pixels which we get on the screen. But what is important here is that, as we discussed, GPU works with really limited amount of information. So like we definitely need to provide information about vertices themselves, but also we can provide information about textures and so-called uniforms. So uniforms is different settings which stay exactly the same for each and every vertex or pixel which is going to be rendered. So this is why they're uniform. And for example, we did this transformation from model space in the world to the screen, and this is how exactly it's handled in shader code. So this small function gets some information about vertex, which comes from CPU side. We can apply this projection view model matrices against each and every vertex, because this function will be called on each and every vertex of the model. And as a result, we need to come up with position on the screen for each vertex. And like we can do really a lot of cool stuff here. But like after we come up with positions for each vertex on the screen, next step of rendering pipeline occurs, which is called actually rasterization. And rasterization is the process of converting of this shape to actual set of pixels. So now we know where exactly on the screen this triangle lives. And this process has a bunch of really cool like special operations. So first of all, you can see that if we store red color here, blue here, and yellow here, rasterizer will automatically interpolate all the colors for all the pixels. Because we haven't provided this information. We only provide information for vertices themselves. But with interpolation, we have all this data, like, which is really handy. And for example, when we spoke about normals, this is like a particular example I really like. If we store normals for each side or like each triangle of the sphere, we will see such shape. Because yes, this is how each side is oriented. But if instead we will fill our vertices with normals, which is like kind of average against like all the common faces here, it will be automatically interpolated by GPU, and we will get such smooth shading here because of normal, which is like really cool. Also, at this stage, if GPU sees that some object is actually overlapping over another object, like it will like pass these shaders to the next step. But if previous pixels were actually over this new like model on new stuff we are trying to render, why bother, like, why to render them? Because we can actually skip them. Nobody will ever see this side of cube, right? So GPU actually strip away this stuff, and like for like this debuffer or depth test approach actually can give us this information in texture. So like it might be handy in future for other effects. And also at this stage, backface culling is applied. As we like started this presentation, performance of rendering is really crucial here. So like why should we render some like internal triangles of the objects when we don't even see them? So like at this stage, GPU can actually check whether we see like facing triangles to us and just ignore all like back-facing triangles to us. And passing only active like pixels which actually need to be updated, fragment shaders will be called. So fragment shader is just a small program like which will be applied to each pixel, like on your like in each pixel this object was affecting. And here we can write any code we want, any processing for lighting, for texturing, like whatever. So like essentially like whatever we want. And if you really want to try it out, there are a lot of services. So for example, this is a shader toy. You can just open this page, write some code here. This is a shader code. And you can produce really insane, beautiful images just with code. And if you never ask yourself, like, are GPU actually like performance? I would like you to share, for example, for modern GPUs, how many of processing units modern GPU have. So like we mentioned that each vertex shader will be called for each vertex, and there are like pretty lot vertices in the scene, and there will be a really huge amount of pixels. But we have essentially like 16K of processing units for each of this function. We can also have like up to 500 texture units, which help us to work with textures completely simultaneously. And like up to 176 rasterization operation like processors of this operation of rasterization and getting these intermediate pixels. And you can compare it with like typical modern CPU of 16 or like 32 cores. This is insane amount of like processing power. So like this is how actually GPU works and GPU renders the image in comparison to CPU. And now with the power of shaders, we can start drawing something more fancy. So like previously we was discussing like triangles, now let's see like this is a sphere, 3D sphere. It's not obvious that this is a sphere just because like we are missing something. And we are missing the key aspect of rendering at all. This is lighting. And lighting is complicated, and there are huge amount of physical models. How can we like calculate lighting and describe it? But the most simple one is like all incoming light, when it hits surface, some like this incoming rays will be diffused everywhere. Some of the color will be actually absorbed by surface, and some of the color will be completely reflected by exactly the same angle. So like having that in mind, we can come up with really like simple but like close to reality views to light. So for example, we can take a sphere, we can put a directional light, which is like, for example, our sun is really too far away, so we can treat all rays sun generate as a parallel rays. So directional light is exactly the same. We have like all the light which come in with exactly like one direction. And in order for us to pick a color for each pixel of the sphere, we need to just compare how normal for each pixel is oriented relative to like direction of light color. And the more like parallel like or like the less angle between of these two vertex will occur, the more bright this point will be. And in rendering or like mass, this operation is called like dot, which finds the similarity between two vertices, two vectors. Also, as we mentioned, like if you gonna look at the object with exactly the same angle, like how light is reflected, you will see this specular blob, really high blob of like high color. And yeah, we also can like simulate this effect with just a bunch of mass, and pretty similar mass. And yeah, just to avoid all these black sides, we can actually add some like diffuse lighting, because like in real life it's really hard to see completely black or completely like not lit side of objects. And then we will remind ourselves about performance once again, that everything we do in rendering should be as performant as possible, and rendering stuff like with full precision is just not practical. So like, for example, if we have a scene and like we have a really distant objects around us, why bother? Like, why render them separately, exactly each like object in the scene, when we can just pick a cube, put ourselves inside a cube, and apply textures on each and every side around us, and we will just get like good enough results. And like, funny enough, you can actually see the stitches, for example, for this cube. So like six sides with textures is enough to cheat you that like there are a lot of stuff around you. Yeah, nowadays like we use sky domes instead, like which is hemispheres here. But like 6 sides are actually enough. Or just another example, like let's imagine we want to render like a brick wall. Yeah, and it looks kind of dull, like, and not interesting. Obviously, we can make a complete 3D geometry or 3D model, and we can put all these little details and like nuances and bumpiness of the surface here, but at what cost? This actually will take huge amount of processing power, like to be rendered at real time. So we need another approach. But what if, for example, instead of putting colors into textures, because like textures are really like cool when we have a lot of pixels and we want to get some extra information for them. What instead putting colors here, we will encode normals here for each and every pixel. And then applying the same approach as we did for like lighting, now we can see how light actually interacts with these like normals. It shades some areas of this brick wall, and it already can look much more visually appealing and visually rich, and it's really inexpensive. And like, to be honest, this technique is not really unique. Like when I visited Vatican City, in like on the ceiling of Vatican Museum, you can see that images actually painted with some shadows around objects. They are completely flat, but when you are standing here, they appear really volumetric. So like you can feel that it's like statues or like whatever. Or, for example, another approach. If you will check objects in real world, as light bounce around, like close like gaps between objects or like corners of the objects will be slightly shady. And it's important that, as we discussed, using rasterization approach, we don't have any information about like close vertices here. So like we essentially only know information about, I don't know, this vertex and this pixel when we render stuff, right? But in order for us to emulate this effect, we need some more information. So how can we get it? And like the answer is simple. We can just bake a texture which will represent, just as normal map, all these shades for this object. And baking also will help us like to save some performance. Or another example. As we saw in ray tracing example, when light bounces from some colored walls, you can see that some part of light actually bleeds to other objects. So this side is greenish, but actually no green light is actually lighting this side of sphere. And the same is true here, that there are no orange lights whatsoever. And like instead of actually calculating all the slide bounces at real time, we can come up with another like caching technique. So like, what if we will put a lot of different points in space and actually cache or like bake all the lighting information at this exact point, like where and which color of light like goes through this one exact point in space. And when we're gonna render any object, we will actually utilize this information to fake that we know like all the light which is bouncing around us. Or, for example, like if you want to have some really like cool reflections, why do it in real time? If, for example, like our skybox or sky is pretty static, so like we can also bake it in like another instance of like, for example, cube map. And instead of finding a color like because of rays, we can actually sample a texture from this cube map for each direction. And we will mimic this effect of like reflection. But obviously it's not real time. Or another example, if you want to render some shades, like, okay, we can just bake this information that, hey, these pixels are not lit. So like, we will bake it into another texture. And if, for example, in future we will try to move this object, you will see how like weird it looks. Because we essentially like bake this information in texture and just reusing it instead of like calculating it again and again and again. But sometimes we really need to render stuff every frame. So for example, really like this example from Resident Evil 7, when you need to solve this like shadow puzzle. And we definitely need to render it each and every frame. And like, how things were really easy in ray tracing. So like, you could just like cast a bunch of rays and get the information that, hey, none of the light actually like gets to this point. But how should we approach shadows in rasterization approach? And actually, we can render stuff to another textures. So for example, like essentially what shadows are. Shadows are part of the objects which are like not visible to the light or like obstacled by like another object. So if we put ourselves from perspective of camera itself, we will be able to render what camera actually sees. We will be able, directional light actually sees. We will be able to store information and distance to each and every pixel here. Then we can render distances from our point of view of our camera itself, and then just compare which pixel is closer. So like if the pixel is closer to light, then it's lit. If it's not, then it should be shaded. And now, using this texture, we can easily apply it to all of our scene and like render some shadows. Or if we really want to do some real-time reflection, so a lot of the objects with, like you can see how many reflections are here. And this is example from ray tracing, because for ray tracing, it's just natural. You just cast a bunch of rays and you see all of these reflections. But for rasterization, we cannot actually do that, right? So for example, if we want to draw a mirror in a game, we essentially fake it. We put another camera behind the mirror to like mimic that we see something like from this perspective. We render it into another texture, and this is how like we get this effect. So like essentially we are drawing scene like 2 times. And nowadays, like modern GPUs actually can combine these approaches of rasterization and ray tracing. So for example, if we want to like We render most of the scene with rasterization, but we apply some ray tracing for only aspects of the scene with like reflections, because reflections are really cool and easy, and like with lighting and so on. And actually, there are so many more cool techniques out there which is used in rendering. But as we discussed today, most of them are based on limited amount of information which is shared to GPU. It's shared via vertices information, via some uniform information, like we can put light direction, light colors, intensities, different textures, and so on. Or we can even like render something into another texture and then use it to render some object. And all other techniques actually based on these exact approaches. And I think this is it from my side. Thanks, everyone.